Hi there, my name is Joao Duro. I'm a research associate at the University of Sheffield, UK, and I'll be presenting about component-based design of multi-objective evolutionary algorithms. And for this, I'll be using the Tigon optimization library. So I'll first introduce this. So multi-objective evolutionary algorithms are been around for a while and are becoming very popular for solving multi-objective optimization problems. You can find them in several software libraries in case you don't want to implement them from scratch. Examples are the PISA and GECCO libraries. And our motivation to this work is to provide a framework for the design of MOEAs that is component-based with a focus on flexibility and reusability. In terms of flexibility, we would like to be able to implement any type of MOEA by using this framework. And in terms of reusability, so we want to be able to reuse the components, and for that we want the components to perform very simple operations or tasks on a set of solutions. Okay, so first of all, what is Tigon? So Tigon is an object-oriented C++ optimization library that forms part of the Liga software. And so the Liga software, which has been published recently in a journal publication down below, is open source, and you can find it on GitHub. And so inside Tigon, there is now this component-based framework for the design of MOEAs. So we have components that are assembled together and in a sequence, and in order to form an MOEA, and this is facilitated by a decorator design pattern, which I will explain in a minute. And during the execution of an MOEA, we can have multiple populations coexisting, and so to ensure that the operators know which population they need to operate on, we use a tag-based approach. So first, I'll explain the decorator design pattern. So design patterns are usually associated with object-oriented programming language, and in this case, I'll speak about the decorator. So the decorator, what basically does, it adds behavior to an individual object dynamically without affecting the behavior of other objects from the same class. So it is considered more effective than subclassing. I'll provide an example now. So imagine that you have created a software and you want to draw a window, and so you create a class called window which has a method draw, and then you like to add features. So let's say you would like to have add a vertical scroll bar or an horizontal scroll bar, or perhaps a very fancy border. So effectively any of these classes you see here, they are overriding the method draw in order to add those features. But let's say you want to combine some of the features, so you could have a vertical and horizontal scroll bar together on the same window, so you need to create another class. And in case you want all these features together, you need to create another class which basically overrides again the method draw. So you can see here the issue is that as I add more features to the window, I may end up with an exponential number of classes in order to cover all these possible combinations. So as an alternative, the decorator design pattern also I'll show here. So first of all, our window class is going to become abstract. So the draw method needs to be implemented. So we create a window-based class, and we implement the draw method on it. So this is a simple window. And now we're going to add our decorator. So this is a class, and inside there is an object which we call the wrappy. So this wrappy object is of the type window, which can also be passed into the constructor. So just note that the window decorator has a constructor of type window, and then there is a draw method, and there is a add feature. So the add feature is important here. So it's the method that is going to be overridden by different classes. So in this case, The horizontal scroll bar is going to implement the add feature by adding its own horizontal scroll bar. The vertical scroll bar is going to do the same, and the border as well. And so now, in order to make this work, what we basically do is we create, first of all, we create an object. Let's say A is an object of type window. So here we are effectively creating a simple window, and then we create new objects, all in a sequence. So first horizontal scroll bar, and then vertical scroll bar, and each time we pass the previous objects into the constructor of each method, of each class. And in the end, when we hit draw, so what happens is, inside the draw method there is a recursion by using our RAPI, and then it calls the add feature method. So effectively what happens is that here is just showing what happens when we hit draw. So first the draw method is called for D, and then it's called for C, and then it's called for B, and then for A. And then what happens is that once it hits A, so A is the last one so it's the first class that it shows, and then after that it starts calling add feature. So it will call feature for class for the object B, and then for the object C, and then for object D. So as it goes through all these classes, it will basically modify it will draw a window with more features. Okay, so now what happens in Tigon, we have a class called IPSet. So this is our abstract class, and we need to create a pset base which implements it, and we have our IPSet decorator. So our IPSet decorator, inside there is an object which is similar to the RAPI, but it's a pointer. Just note that. And so underneath the IPSet decorator, we could have different classes. In this case, they are our operators. So here we will just show this is a XVX crossover, scalarization, and randomly. So these are all different operators which will represent the components of our MOEAs. Okay. So inside our evaluate, again, we have our recursion, and then we have our evaluate node. So let me show you now how it looks like. So this is an example, this is an algorithm called NSGA-II. So in here what we see is the first 4 lines are actually not part of the algorithm. They are just setting up this workflow. So first of all, we have besides the pset base, we have a problem generator that initializes the problem, and then we have a random init which initializes a set of solutions, and then we have evaluator which basically evaluates those solutions. And from line 6 into line 13, we basically have the operators that form the algorithm, the NSGA-II algorithm. So they will all be run in a sequence, and this all starts by triggering line 15, which basically calls evaluate of the last operator, and then it will all go in a sequence. Once we call the evaluate method again, it will run another iteration of the algorithm. So this is available online. You can see this code in GitHub. Now let me talk to you about sets. So basically what happens is that each operator can create, for instance, the operator could create solutions, and these solutions are then stored into sets. So sets is basically a collection of pointers to solutions, and solutions can belong to several sets. So let me just show you an example here. So let's imagine we have several solutions. They have been created already, so they are somewhere in the memory. Now let's see an operator. So one operator here, for instance, creates one set, and so that set could contain all the solutions which have been created so far, as we are showing in here. But another operator could create several sets, and these several sets they don't contain the solutions, they contain the pointers to the solution. So they could contain so you could see here, for instance, that set 2 and set 3 they actually have the same solution inside, so they are pointing to the same solution. So that's solution 60. It's shared between set 2 and set 3. Okay, so now let's talk about tags. So what are tags? So tags are basically labels that are attributed to sets by operators. Tags are used to help operators find the sets that they need to operate on. And for an operator to operate on a set, the set needs to contain all the tags that the operator is looking for. And also the operators have two lists of tags, right? So what happens is that there is an input tag list where the operators are using the sets as read-only, and there is an output tag list where the operators modify and create the sets. So let me show you an example here. So first of all, here we are looking at 4 operators. Now the first operator is going to create a set and is going to tag this set with tag 1. So operator A in this case has an output tag, and the output tag is tag 1. Now operator B is going to read from the set or the sets from operator A, so it needs to have an input tag, tag 1, and because it's going to create new sets and is going to tag them with tag 2, right? So it needs to have an output tag called tag 2. And then what happens is operator C is going to operate on the sets from operator A, so it has an output tag of tag 1. So just see here, the operator C modifies the solutions which are on those sets from operator A. And then the same happens with operator D, but operator D also reads from the sets from operator B. So operator D has an input tag which is tag 2 and has an output tag which is tag 1. So basically what happens here is that operator A creates some sets which are then read by operator B. Operator B then creates new sets, right? And so operator C then operates directly on operator A sets, and operator D also operates on the sets from operator A, but it does so by first reading the sets from operator B. Alright? So what also is important to note here is that we also have, so the sets which come from operator A have been created. So operator A has a filled circle just to indicate this, and as opposed to operator B, which has a non-filled circle. So it just means that operator B, it's not going to, so although it creates the sets, but it doesn't create the solution. So it is just rearranging the solutions from operator A into new sets. Okay. So now let's show you with an algorithm. So here with an SG2, here initially we are going to create a set which we call the main optimization set, and so it creates, so initialization operator creates solutions and stores them into pointers in a set, and then the evaluator modifies the solutions by evaluating. So the non-dominance ranking operator takes those pointers and arrange them in new sets according to their rank, and then we have the elite NSGA-II elite selection, which knows which solutions should go into the elite population because they are organized by ranks. You also have before the elite, there's also some crowding, an SG2 crowding, which basically it's modifying those sets from non-dominant ranking. So eventually the LSG2 selection algorithm, then after creating those sets, they are read by tournament filtration for direction, which then creates new sets. So these new sets, you can call them the child population that comes from the tournament filtration direction, which are then sent for crossover, polynomial mutation. So at the end, you have two populations here. So the one coming from the elite selection, which is the elite population, and the child population coming from the tournament filtration for direction, which are then merged together. into this by the operator merge for next iteration, and then they are used to replace the main optimization set. So this will happen on the first iteration, and then once we call the evaluate method again, it will call it. This whole will happen again the same, and basically the main optimization set will be updated each time. So this is just an example. So here I'm just showing you. So if you want to add input or output tags to the operators, you can use the add input tag or add output tag method. So this is just showing you. This is just specifically for NSGA-II. So it obviously it will be different for different algorithms. It just show you how you can, from the object of each operator, you can use those methods. And so now let's show you how to implement different types of MOEAs. So first of all, you can find different implementations on GitHub. And so far I've shown you how it works with an NSGA-II, which is an elite Pareto-based MOEA. I'll just show you roughly how it works for other ones. So for MOGA, which is a non-elitist Pareto-based MOEA, for SMS-MOA, which is a steady state indicator based, also for MOED, which is a decomposition-based MOEA, and for Perigo, which is a surrogate-based. So first of all, NSGA-II, I'm just comparing NSGA-II with MOGA here. So we can see that because they are both based on non-dominance ranking, so they both share the non-dominance ranking operator. So NSGA-II actually does crowding, he does elite selection, but MOGA instead he does something else. So he has operators such as average fitness, shared fitness, stochastic universal sampling, but they both share the same principle that you should create a child population, and so they use similar operators. Although NSGA-II uses termant, and MOGA uses a random approach. So looking now into different algorithms. So on the left again we have MOGA. I'm just comparing it with SMS MOEA, which is on the right. So they are both using dominance ranking, and the main difference here is that SMS MOA has its own specific operator called SMS MOA reduce. So SMS MOA reduce will use hypervolume, will calculate hypervolume, and then it will use this as a criteria to see if a solution can go into the population or not. And SMS MOA also is so it's a steady state algorithm, so it means that only one solution is created per iteration. So that means that we could customize its operators in order to have different behaviors, such as you can specify how many solutions you could create. And here, so I'm comparing two algorithms. So in the left we have MOED. So MOED is a different type of MOEA. So it's a decomposition based. So it means that it needs to create weight vectors. So one of the operators is a weight vector in it, and then there is scalarization. So for each weight vector, it scalarizes the solutions, and so because it has different single objective problems. And then MOED has actually a quite complex neighborhood criteria. So basically, here we are creating different sets, putting them into different neighborhoods, and depending on different criteria, then the solutions are allowed into the neighborhoods or not. So you can also see at the end that there is some crossover and there's some polynomial mutation. Then on the right we have a different type of algorithm, which is a surrogate-based type, and so we can see here that as opposed to weight vector in it, we have a direction iterator, which is somehow similar. So it also relies on different weight vectors, but it's a different type of algorithm. It's a Bayesian type of algorithm. So it also relies on scalarization, and then it has an operator called surrogate-based optimizer that basically solves a single objective problem and finds a solution. So and that's it. So we like to conclude that this framework, this component-based framework for the design of MOEAs offers sufficient flexibility to implement a range of MOEAs covering different paradigms in evolutionary computation. We expect that as more algorithms are added to Tigon, more operators become available. It will become easier to design new algorithms by reusing existing operators. And for future work, we are considering other metheuristics, not necessarily evolutionary algorithms. It could be particle swarm optimization and simulating annealing. And we like also to extend the current framework to find novel algorithm designs by exploiting automatic algorithm configuration methods. And this is based on the paper we see below. And so this concludes my talk. Thank you very much for listening, and if you have any questions, please email by email below. Thank you.